Hello everyone. In this video, we are going to look at different functions that are available in Deep Learning Toolbox in MATLAB. So if you want to form a neural network and train it and do predictions and so on and so forth, partition the data, change the learning rate and all those that I have explained in my previous videos, all these terminologies, but mostly use TensorFlow for that. So if you want to use MATLAB, I want to show you which commands to use and then show you different examples for function approximation, CNN, RNN, if you want to do a manual update, if you want to manually form a network by adding layers, making parallel branches. So I want to show you all of those, so stay tuned. The first thing we want to do is a simple function approximation with a feed-forward network, okay? So here, let's say we want to approximate this sine function, which has data from -2 pi to 2 pi 5,000 data points. One of the first things that you typically do in training is you hold a portion of the data for validation. And this can be done manually by the rand_perm command. So basically get some indices on random and then assign like 80% or 70% of them to training data and like 20-30% to validation data. Or you can use this built-in command called CV partition. And here you pass to it the length of y or x in this case. They are the same. And then you say hold out 0.2. What does it mean? It means keep 20% of the data for validation and the other 80% for what? For training. It gives you these indices, C, and once you pass that C to the function training and to the function test, now these are going to be exactly the indices inside X and Y that you want to allocate for X and Y. So the C is not exactly index. This determines which side, which parts of the data, if you look at it, C is not really an index. But if you look at like this, training of C, let me run this for you. So training of C are what? This is a logical array where ones are the trainings and zeros are the test. Okay, you see that? So, but if you look at C itself, C is different. C is what? As you can see, C is a variable which is called CVAR partition variable. Okay, so you have to apply these functions to it to generate the logical array. So here we go. X train, Y train, X validation, Y validation, 80%, 20%. If you want, change this number. Many times we go with 0.3 instead of 0.2. Now it's time to define your network. So here we use basically different types of layers, and then we concatenate them, we put them together by this bracket, and we form the network, as simple as that. So what kind of layers do we need here? The first layer we need is to take the values, the inputs from the features from the inputs, right? So that layer is called feature input layer. And in this case, the number of features that you have is 1. All you have in your X is just a scalar. X is not really a multi-dimensional vector. If it was, you have to change this to the dimension of the features. And then also you activate the normalization for it. So not only you receive those features from the input layer, also what you do a normalization, apply data normalization, which is very, very common in neural networks. Okay, and there are other options. We can get to them later, but another thing that is common for all layers is you give them a name. So here the name of this, I call it the input layer. So this one receives the inputs from X, and now you connect it to a fully connected layer with 20 neurons, okay? And the name of it, we call it FC1, fully connected 1. Then you pass the output of that to what? To the next layer, which is a ReLU, or ReLU function, right? And you all know what ReLU is. If not, watch my previous videos. So for negative x's is 0, for positive x, it's just x. And so it's like a broken, basically, or truncated linear function or identity function. And that is very common when you do regressions in neural networks. ReLUs are very, very common. So here we do a ReLU, and on the result, the output of the fully connected, and then we keep adding more hidden layers. So we add another hidden layer by another fully connected, another ReLU, another fully connected, another ReLU. Okay, so we have several hidden layers here. And finally, after the last ReLU and fully connected layer, now we add the last fully connected layer. As I said, that is only one this time instead of 20 neurons. We do one. Why? Because our output that we want to compare against is just one single number. It's a scalar. So here we make sure that it has one neuron, and then we pass it to a regression layer that basically generates a number scaled appropriately, similar to what? Similar to the output. Okay, so here you have to undo those normalizations and so on to get back to the appropriate scale, so you can compare the outputs against the labels, and so you can have a meaningful loss function calculation. So this is a simple neural network that, as I said, is formed by putting several layers in series. And now we can use it for training. Now, before we go to training, I want to emphasize a few other things. There are other layers that you can use in neural networks. In addition to this activation function ReLU, there are other ones. One of them is called tangent hyperbolic layer, which is called 10H layer, and that is very common too. The 10H, the good thing about it is it's not basically, it's a smooth function. It's not like ReLU that has no derivative at 0. There is this guy called clipped ReLU, which is another interesting thing. So this one, basically, after some x, it is going to be saturated at some fixed number. So at negatives is 0, between 0 and some x, it's x, but after some x, it's going to be saturated. There is leaky ReLU, which at negative x's is not 0, it's just a scale, a number times x. So it has two lines. One is on the right side, y equal x. On the left side, it is the scale times x, and this scale is typically less than 1. And we also have another smooth function called swash activation function, and this is the activation swash, okay? X over 1 plus e to the negative x. Clearly, when x is going to positive infinity, it goes to positive infinity. When x goes to negative infinity, now you go to 0. So that is called a swash function, and that is another custom function that you have, okay? Similar to tangent hyperbolic. There are other functions too in general, but these are the built-in ones in MATLAB. Another type of layer that you might use is called batch normalization layer. And what the batch normalization does, as the name says, is normalizes a batch, and it does it for each channel independently. The good thing about it is to speed up the training of the convolution neural networks and the sensitivity of them to how you initialize the weights and biases. The batch normalization is exactly the type of thing that we use. And I explained that in one of my previous videos. If you watch, I have a video, I explain batch normalization. So if you, most of the time you use it with convolution neural networks and between convolution layers and nonlinear layers like ReLU or any other activation function. In between convolutions and the activations, you use a batch normalization. So you can speed up the training of the CNN network and reduce the sensitivity of it to how you started the weights and biases. Okay, there is softmax layer, which is basically gives you a probability distribution. It is used for multi-class classification tasks. And there is the classification layer, of course, which is used for classification tasks, and typically it calculates cross entropy for classifications. And the classes have to be mutually exclusive, of course. The other important thing about this classification layer is it infers the number of classes from the output size of the previous layer. That's why here, look, we didn't do classification here. We want to do regression. But here, by the output of this fully connected layer, I'm telling the regression that, hey, the output should be a scalar, okay, because I'm using one neuron. You do a similar thing for classification. And we have flattened layers. This is when you want to collapse the dimensions, right, into a channel and do dimensionality reduction here, basically. And by dimensionality reduction, I'm not talking about principal component analysis or anything like that. I'm not talking about feature dimensionality reduction. I'm talking about reducing the dimensions on a output of a layer. Another layer we have is called dropout layer, which you give it a probability of dropping weights and biases on random. And this is really useful for when you want to avoid basically overfitting. So that is common too. Then we have another thing called average pooling and max pooling. Okay. So we have the average pooling and max pooling. Let's see if I showed the max pooling somewhere. Seems like I didn't, so I should add that. So another way that you reduce the dimensions of the outputs is to do average pooling on the blocks, or you do what? Max pooling. And here you have to provide a pool size as the first entry, and then a padding and a stride. Okay, and padding is the overlap between the windows, the one window and the next one as the window moves across the data, and a stride is the amount of displacement. So you can have average pooling 1D, there is 2D, and there is what? There is a max pooling layer. Let me just add it here for sake of completeness. Okay, so this is the max pooling layer, which is again 1D, and there is more than that, and the explanation of that is very similar to this top one, except, as I said, this is the max pooling layer. Okay, so now that we have seen these different types of layers that are common in neural networks, okay, we want to go ahead and let's say plot the network first. Now that we form a network, let's look at a visualization of the network. We're going to plot it. So the command that you can use is called analyze network, and not only it plots, it also analyzes the network. So you pass the network or layers to it, it shows you the plot. So you know what, before I move on to training and everything, let me run this portion of the code so you see the result of that, and then we go from there. So let's go ahead and run. Let's do it one more time. Seems like I did not really press on the button. There we go, F9. There we go. So if you look here, you have your network starting from inputs to fully connected 1, ReLU 1, fully connected 2, ReLU 2, fully connected 3, ReLU 3, fully connected 4, and output, which is a regression. And you see the description of these and the size of the weights and biases, whether they have anything that can be learned or modified. You can see that here, right? And here you have C and B. C means the number of classes, and B means batch size. Okay, so if you see that here, and the output, as you can see, the function that is going to be used is mean square error, MSE. So and this error, in this case, you can ignore it, that's fine. We need the output layer to do the training. Okay, so don't worry about that error, it's not going to do anything in this case. So that is our network. Now we need to provide the training options, right? What is it that you want to do? So here is a sample set of options for training. The command is called training options. The first thing you provide is basically the solver. What kind of solver do you have? Is it Adam, is stochastic gradient, or whatever it is? You provide the solver. Then you give it the max epochs, okay? And I have defined all of this in my previous videos, what is epoch and so on. So 200 max epochs, initial learning rate at 10 to the negative 3, And then in this case, since you have validation data, you have to specify that in the training option. So you say my validation data is xval and yval, and you put them in braces. And validation frequency 50, and then verbose, which means showing the results, typing them in the command window, is false. Don't do that. But for plots, I want you to show me the training progress. Okay, and there are more options here. One of them is called learn rate schedule. So if you want your learning rate to change and adapt during the training, instead of none, which is the default, and here basically we have not provided it, so it means it doesn't change, it's going to stay at this number. One of the things you can do is call this guy piecewise. And in piecewise, your learning rate is going to change during the training at the specific intervals, and typically as you go toward the end of the training, the learning rate will change, right? And it can go basically smaller, right? So you start faster and then go smaller, decrease over time. And there is another one called warm start. So there is another option that is called warm start here. And basically this is based on a previous training state. The learning rate will be adjusted based on the previous learning rate. So that option also exists, but most of people might go with piecewise. So that is one of the things you can do. The other one is the size of the batch, mini batch size. If you want, you can provide that, or MATLAB will decide by itself. Another thing you can specify is momentum, and I define momentum in my previous videos. It's typically used in stochastic gradient methods or gradient methods, that the change in parameters is affected by how much they change in the last iteration as well. So you can do that. Another thing you can do is basically provide metric or metrics, and this is how you want your system to look at the use of the validation data and basically the loss function. Okay, so here these are more options if you want to use them. So in this case, we use these options and we kept some of them off or by default. Then it's time to train the network. In this case, the network is very simple. It's called layers. You provided the X train and the Y train, right? Or the features and the labels, the layers and the options. Another thing that you can provide right behind the options is the loss function. So here you can provide the loss function. You see the loss function was MSE, means sum squared, or mean of squared errors, I'm sorry. Or if you don't, as I said, MATLAB will decide, but you can, if you want to use a different loss function, you can what? You can go ahead and do that. But typically, the loss function is determined based on the network, specifically the last layer, which tells it whether it's a regression problem, a classification problem. Like if it was classification, it would probably use cross entropy instead of sum square error or min square error or anything. Okay, so this loss function is one last option before this, or one to the second to the last, right? Second to the right option that if you want, you can specify. So here the network is trained. If you apply this command, and all the weights and biases will be adjusted. So the minimum loss function is achieved during those epochs. Now that the network is trained, you can pass it to this function called predict. And this predict was the same predict that we had in machine learning, but here, of course, is used for neural networks. So you pass the network to it and the test data. And here for the test data, we generate some data in the same range, 100 data points, and predict them and call the predictions Y predictions. So now we're going to plot the training data and the test data. Or sorry, the test data with actual labels and the test data with predictions from the network. We want to see how good the system is doing on the what? On the test data, right? How well it has learned the sign function with all of these neurons in the hidden layer, right? So here we go ahead and run the whole code. So this is the structure, and I showed you that. Now this is that plot. Okay, and you clearly see your loss function is going down. And in this case, you have 6,200 iterations. Okay, and there are 31 iterations per epoch. So 31, 6,200, right? If you divide that number by this, guess what? You're going to get your 200 epochs. And you have the validation frequency and everything. And now, as you can see in the loss function, you see that not only the loss function on the training data is going down, but also it is going down on the validation data continuously and never jumps up. So you're not doing any overfitting here, although you have not used any dropout layer or anything, but clearly your validation loss function never jumps up, so you're not doing overfitting here. Okay, although you might get away with smaller number of neurons or layers, but here clearly you're not doing overfitting, and you should expect a good result. Let's see. So the training is done, and you can see that your network actually did a very good job, relatively good job. There are some small discrepancies here and here, but your network approximation and the actual Y's of this test data are actually matching very well. So you could approximate your sign function by a bunch of fully connected networks and ReLUs. Okay. And if you want probably smoother functions, instead of the ReLUs, you might replace them with tangent hyperbolic, which is a smoother function, or the swash, and see if you can get better results. Okay, so this is function approximation and some of this. Now for convolution neural networks, typically the input layers are images. So the first layer we want to use is called image input layer, and you provide to it the size of the image, right, 28 by 28 by 1, and you give it a name like input. Then you pass them to convolution layers, and this convolution, typically for images, of course we use convolution 2D layer, because there is also convolution 1D, and convolution 1D is for 1D signal, not images. So for images we use convolution 2D layer, and 3 and 8, right? So here we are providing the specifications for the convolution layer, and for padding we say the same size, and name of it we call con1. So if you're wondering what is 3 and what is 8, let me add them for you as a comment here, so you have a better idea how to use this command here. Okay, so the first one is the filter size, and the next one is the number of filters. So the filter that you're using, the convolution filter, is 3 by 3, and you're going to use 8 of them in this layer. And then between that and the ReLU, guess what? As I said in the previous code, you're going to use a batch normalization to speed up the training and reduce the sensitivity to initial conditions. And then here you start dropping the dimensions by a max pooling layer. But what kind of layer? 2D max pooling. Remember the one that I showed you in here? It was a what? It was a max pooling, right? Let me see here. It was 1D. But for images, you have to use what? You have to use a 2D layer. Okay, and again here, that is the size of the pool, then the strides if you want, and the name. Then you go for the next convolution, this time 3 by 3, but 16 of them, right? So as you go on along the convolution neural networks, typically you increase the number of filters, and you create more smaller number of convolved images, which you might call the extracted features. And another batch normalization, another ReLU. Then we go for a fully connected layer with 10, and a soft max layer, right? And the reason that is here, you want to have 10 different classes. And finally, what? A classification layer, because you want to have 10 different classes in this case, right? And give it that. And that's all it is. This is your layers or network. Again, you can plot it if you want. You provide options here. Again, Adam, 15 epochs, initial learning rate, no verbose, some plotting. This time, the training data and the test data and everything are completely random, but you can change these random things with whatever you want. Okay, so here, if you look at the data are random images of 28, 28, 1, and 100. So if you look at these images, these small images, they are going to be like noise. They are not going to be real images. But feel free to read images here. The important thing is these input images must be this X if it's the set of all images. The format of it should be a 4D array, okay? So it should be m by n, the dimension of the image, 1, okay, which is grayscale, and then 100, which is the number of images, number of samples. And here the output is like going to be 100 by 10. Because you have 100 data points and data or images and 10 classes. And then you train the network on those with the layers and the options. And then here, to make predictions, you're not going to use the command predict, because predict will generate numbers for you. Here, use what? You say classify, not predict. Okay, because here you're doing classification. Again, what you need to do is to change this part to include actual images. Maybe you need to do partitions or anything, and then you can do plots and so on. And I have done all of those in TensorFlow. So here my goal is not really to show you a real image, but rather how you form these layers in MATLAB and how you use them. So here, let me run this also for you. And you can see that this is my layer, as you can see, conv bash normalization relu, and so on and so forth. And again, you should be able to see that the loss function is going to drop. And here we used a few number of epochs, of course. It is dropping. We can add a lot more to it. And that's what you typically do. But for bigger images and a lot of images, which you typically do for computer vision tasks and deep learning, you want to have GPUs, okay? So here I'm skipping all of that, and this is the structure of my network. The next type of network that you might use for analyzing sequences, and you need basically memories, are RNNs, recurrent neural networks, which there is feedback and there is memory many times. So here, one of the inputs that I use for this layer is called sequence input layer. So do you see different input layers that we are using? For regression, the layer we use called feature input. For convolution is called what? Image input layer. And for recurrent, we use sequence input layer. Okay, and then here we have what? Again, a number, which is the feature dimension of the input data, and then a name and input. Name of this layer is called input. Then here we use the LSTM layer, okay? And I explained LSTMs in one of my previous videos, so I'm not going to go over that. And of course, the first input to it is the number of hidden units, 50. And then the output mode of this LSTM could be either last, which means the last data of the sequence, or it could be sequence, which is the entire sequence instead of the last number of the sequence. The name of it is called LSTM. So this is the second layer after the sequence input. You connect to a fully connected with 10. You do a softmax and a classification. So here, right, you have 10 classes, and your sequence is going to be classified as one of the 10 labels or one of the 10 classes. And again, you can analyze the network, you can provide training options. And here some training data is created and then passed to the network for training, and then a classification again is done. So this is going to do something similar to previous one, because the data that I have created here, the sequence, are basically again random numbers. So this is not going to be really meaningful. But if you want to predict the future values of a sequence of data like stock market or anything like that, then this is the place that basically you can import your own data here instead of these random numbers. And this was the training here. Again, you see the loss function dropped, and we only use 200 iterations. We can use a lot more. And there is no validation here, but you can always break down your data into validation and training. Okay, so that was RNN, the type of layers that you use in it. Now, all of this, if you looked at them, the network is done by simply defining some layers all back to back in series. And then for training the network, we use the command network train right here that you have. Train network, and of course we have the training options, right? Very simple, and predict or a classify command. Now, sometimes the network is more complicated, the type of data, the kind of work that you do. So instead of this built-in function that does all of the training and everything for you with a single command like that, you want to do the training manually. If you want to do manual update, there are some other things that you need to do. So here I'm going to go about talking about those things. So in those cases, what you need is to combine these layers that you made, convert these layers into what we call a deep learning network using the command called DL network, as I'm going to show you. And you can see it right here. So look, I created all these layers, and then I convert those layers into what? A deep learning network using DL network. And the type of arrays that you use for training, you don't typically use regular arrays like you did here, right? What you will do, you use DL arrays also. And let me show you that here, which is deep learning array. So you pass deep learning arrays to deep learning network, and the loop that you do, the training loop, is a loop that you write yourself, a for loop like this. Okay, so you don't use that network train command anymore. You do the training all manually through a for loop. When would you do that? As I said, when you have a customized training loop. For instance, you want to have custom training loops, like control the forward or backward passes manually for a recurrent neural network. If there are complex architectures, if you want to have your own cost function, if you want to have your own learn schedule, right, for learning rate schedule, anything that you want to do beyond these built-in functions, it's more complicated, you want to make it customized, you do it manually yourself. Or your architecture of the network is dynamic. What does dynamic means? It means the data, especially in RNN networks, the input sizes change during the training, because these guys, these train network on X train and Y train, it expects kind of a stationary X train and Y train and not changing it. Okay, or even if it's in RNN, it expects at least the dimension of the data to stay constant. If they are variable during the training, the system is dynamic, then you have to use a manual loop. So let me show you how to do that. So here, let's say we want to do it on the regression problem. So again, basically approximating the sine function. And the layers we have is very similar to last time. We have the input layer, fully connected ReLU, fully connected ReLU, fully connected ReLU, and fully connected. And we can add a regression layer at the end if we want to. Okay. Now, in this case, we are okay just in this case because y is sine of x, so you are between -1 to 1. But it's a good idea to add one of these regression layers at the end. Okay. Now, the first thing we do, we connect the layers, convert the layers into a deep learning network using this command. Now, this guy, I can use in manual updates. The training options, the number of epochs is 200, the mean batch size is 100, learning rate is 0.01. The losses, if you look, initially you start them at 0 of the number of epochs and 1, but as you move on, you're gonna update these losses. So this is a pre-allocation, basically. That's what it is. Now look at the training. You go from epoch of 1 to the number of epochs. What is it that you do? You first shuffle the data, then you loop over mini batches. Okay, so you see here, you have loop within loop, right? So one is for epoch, and then inside epoch is the mini batches. So you get your mini batches of X and Y, convert them into deep learning arrays by DL array, and you have to make sure the dimension that you pass is correct. In this case, you have to transpose the dimension, because the dimension that the system is expecting is 1 by batch size, not batch size by 1. So here, by saying CB, you are doing the transpose of that. And what does C mean? What does B? I mentioned them. C means channel and B means what? Batch size. Now in this case, you only have what? One channel, so C is 1 and B is the batch size. Originally, the dimensions that you generated here, if you look at it, it was batch size by 1. So you have to convert them to 1 to batch size. So you can what? You can use them and pass them to your loss function. Okay, how would you evaluate the model gradients, and how would you calculate the loss function, update the loss function or values, and how would you update the weights and biases of the network? So here we have two built-in functions. One is called the model gradients. This is your utility function, the one that you wrote, the custom one. And the other one is this guy, SGDM update, okay, stochastic gradient update function that you write. And you can write whatever you want in these two functions. And now you use that function with the network and the training and the labels, pass it to DLF eval. That will give you what? Gradient and the loss. These are the outputs of that function. Also pass this net that you have with the gradient that you got from the previous step and the learning rate, and that will update the net to the new net or changes the weights and biases. So now if you look at these two functions, these are written down below, and you can write whatever you want. How is it that you calculate your gradient? This is your chance to write your own gradient calculation. How would you update the learns and biases? This is your chance to what? To update the learns and biases. If you want to do learn rate scheduling or anything, you can put it here as well. Here, you see. So here, see, parameter name is learnables parameter I. Parameter grad is gradient. Net learnable value is whatever it was minus learning rate times the gradient, right? So this is the simple steepest descent algorithm. And as I said, this learn rate that you get it as the input, inside this, you can change it, or you can write another utility function that does the learn scheduling. Okay, learning rate scheduling. So this is completely under your control here, how you want to do it. You see there is no momentum here. You can add momentum the way you want. You can do anything you want here. The same way here that the loss function is MSE, but if you want to define your own loss function, you can do that. If you want to calculate your gradient any way you want, you can do it here. We are using the built-in function DL gradient. But if you want, feel free to change it to anything. Then this allows customization. So now that the net is updated and the gradient and loss are updated in each loop, when the loop is over, the training is over, then the losses at the end of epoch are equal to loss. And then if you reach the end of the epochs, then you're going to stop. And finally, you plot the losses, and then you generate some test data and use it to pass it to the predict. And again, if you look at your test data, again, you convert it to DL array before passing it to what? To the predict, and get the Y predictions, and then plot predictions and the labels of the test data to see how good you're doing. So this is all done in a custom manner, and everything is done with a for loop, all manual. And here, let's go ahead and run that. Right, so here you don't have the option for verbose, you don't have the option for plotting or anything. You have to do everything yourself. Okay, and this is good when the problems get more complicated and more customized. So here you see, this is the only verbose that you have, and you added it yourself here, right? when you say display epoch num spring loss equal this is exactly this line. And it keeps updating per epoch, so 100, 200, it goes all the way to the number of epochs, which is 2000. And hopefully at the end of it, you wrote these utility functions right so that you get a good result, right? So I'm gonna stop the video here, wait until this is done, show you the final result, and then we go to the last code. Okay, so the epochs are over. This is the loss function that you see it is going down. And this is what the approximation, which is done relatively good. Okay, there are some discrepancies here, but it's not really bad given that our network is not very complicated and it does not have a ton of layers and hidden, the neurons in the hidden layers. Finally, we go and look at if you want to create a complex network. For instance, it has two branches, parallel branches. How would you do that, right? So for that, you can use this guy called addition layer. And I'll show you how to do that by using these commands called add layers and connect layers and this layer graph. This is another way that you can make your network very complicated. Instead of a simple feed-forward, simple CNN, or simple RNN LSTM network, if you want to make it custom network and connect the blocks, these layers, however you want, the nodes, how would you do that? So here, let's say I create some layers, layer input 1, layer input 2. These are two input layers for the inputs images, okay? And then each one of them will later be connected to a convolution layer, conv1 and conv2. So input 1 goes to conv1, input 2 goes to conv2 in parallel. And then here we're going to add an addition layer to add these two parallel branches together. It takes two inputs. And then we connect the output of that to a fully connected layer, a softmax, and a classification layer. Okay? So here we just created these layers, and we did not put them in a bracket like we did in the past to create these layers, right? So we have no network right now. We have individual nodes, individual network, not the whole network. So the way that you connect is this. First, you create what a layer graph, a neural network graph, okay? How? Using the command layer graph. So you say the layer graph is layer graph of input 1. So a layer graph, as here you can see, represents the architecture of what? A network where each node is a layer and each edge is the connection between the layers. So first you update it, start it. Basically, this is the initialization of that entire network, which we're going to call L graph. You start it with layer graph, then you say what? Then you add to it, add layers input 2, you connect it to it. Then what? Then you add conv1 to it, you add conv2 to it, you add the add layer, the fully connected softmax and output. Is that it? No, because here we have not yet defined how these layers are connected. All we did was added all of these layers to what? To the layer graph. Okay, so this part here is something similar to that bracket, except the order of connection is not determined yet. We just put them in some graph. We just say this graph has all of these layers in it. Okay, we added them. Now, how do we connect? This is the next part. This is the important part. You say, well, look, the input 1, the output of this layer called input 1 should be connected to what? To the conv1. The output of layer input 2 should be connected to conv2. Then what? Look at this part. The output of conv1 should be connected to input number 1 of the add layer, this guy. this add layer, which has two inputs, the input number 1 of that should be connected to the output of conv1. The input number 2 of that should be connected to conv2. You see here with forward slash after the name of a layer, we are talking about which inputs of that. You see, so now I'm bringing the two branches into the add layer, connecting them individually, and then the output of the add goes to fully connected, the output of fully connected goes to softmax, the output of softmax goes to the final output layer. So this is how you connect the layers together. First define them, then put them in a layer graph, then define the connections. And now you can do what? You can look at the network. So let me run this for you. So you see the parallel branches. Now here, I'm not going to run it on any data or anything because that's not the goal here. The goal is to show you how to bring these two parallel branches and then connect them for the rest of the network. Okay, so this is the custom network. So in this video, I showed you all of the important functions, right? And used 3 examples. For function approximation feedforward, CNN and RNN, I showed you how to create a custom network and how to manually update the network with custom gradient function and custom loss function, okay, and update function for the weights and biases. So hopefully this video summarizes all of the important things you need to know about deep learning deep learning or formerly neural network toolbox of MATLAB, and how to use these commands to achieve your goal. Thank you so much for your attention. I'll see you in the next video.